Please allow me to warmly welcome you on the occasion of the Semmelweis Budapest Award. With an almost 250-year-old tradition of academic excellence, Semmelweis University is widely recognized as one of Europe's leading centers of medicine and health sciences, combining innovation and tradition in three main areas: education, research, and health care. However, in addition to this triadic priority system, we also take pride in recognizing extraordinary achievements to promote science and show guiding examples to younger generations and experienced researchers alike. With this objective in mind, the Senate of Semmelweis University established the Semmelweis Budapest Award in 2009, an award that is our institution's highest attainable international scientific honor. The award recognizes the achievements of world-renowned and accepted international researchers working in the field of natural sciences, whose research activities have produced internationally acknowledged results, and whose work contributes significantly to our understanding of living natural science, and to benefit the humankind. No need to say, all the candidates had to show a very strong devotion to Semmelweis University, which can be reflected in intensive scientific collaborations and other living connections and relationships. 7 exemplary scientists have been presented the award since its establishment. At first, in 2010, Professor Jeremy Nicholson was awarded in recognition of his groundbreaking work in metabonomics, which has contributed significantly to the development of new diagnostic methods. In 2011, the university's highest scientific honor was bestowed upon Professor Sir George Rada, the Hungarian-born father of magnetic resonance imaging examinations, as well as a remarkable fellow of international science policy. 5 years ago, Professor Péter Somogyi, another famous scientist of Hungarian origin, received the award, recognizing his pioneering research efforts of the chemical identification of neuronal types and the localization of signaling molecules in identified microcircuits. It was in 2013 when we have awarded Professor George Olah, the Nobel laureate chemist who had started his career in Budapest at the Budapest Medical University. At that time that was its name. He has developed a promising new approach to solving not only our long-range dependence on decreasing fossil fuels such as oil, gas and coal, but also to mitigating global climate change warming caused significantly by greenhouse gases like carbon dioxide and methane. Another year has passed, and in 2014 the Semmelweis Budapest Award went to Professor George Klein, who was not only world famous for his outstanding cancer research, but also for his essays and unforgettable thoughts on the theory of science. His books have been translated into Hungarian and are among the bestseller works depicting the problems of present-day science. We are very proud that he was also one of the famous Hungarian-born scientists who has got the opportunity to influence world science questions. It is extremely sad that these two wonderful personalities, Professor George Olah and Professor George Klein, are not among us anymore. In 2017, this year, they have passed away in Stockholm and in Los Angeles, respectively. It is our great respect that the remains of Professor Olah have been buried in Budapest. Professor Thomas Högfeldt. His lifelong achievements of chemical neuroanatomy are worthy of any prize. It is a great honor for Semmelweis University, as well as for us personally, that we could confer this award on Professor Thomas Högfeldt 2 years ago. And we were all amazed at his modesty and wisdom as he came out with his groundbreaking results in neuroanatomy. Last year, the recipient of the award was Professor Stefan Hell, who currently is the world's leading scientist in nanoscopy and high-resolution biomedical imaging. He is the recipient of the 2014 Nobel Prize in Chemistry for his work, in which the inherent optical microscopic resolution limit was surpassed by the use of fluorescent molecules and a spatial illumination technique he developed. And today, the list of the awardees grows once more, and Semmelweis Budapest Award's prestige, importance and relevance increase on this spirit-lifting occasion. It is my great honor, pride and pleasure to announce that the 2017 award goes to Sir Ravinder N, who currently is Emeritus Professor of Rheumatology at Imperial College, London, and visiting professor at Oxford University. Professor Maini's professional activities are linked with several ties to Budapest and the Hungarian scientific scene. The Kennedy Institute of Rheumatology, previously led by Professor Maini, has been providing scholarships to many Hungarian researchers, enabling the Hungarian medical community to get a first-hand opportunity to learn about the new therapeutic options in treating inflammatory diseases. Professor Maini has been maintaining close professional and personal family relationships with many Hungarian researchers. As part of this relationship, in autumn 2013, he was the honorary guest of Semmelweis University's most important scientific event in Budapest, the Semmelweis Symposium. Naturally, it is no need to say that following the recommendation of Professor Maini for the Semmelweis Budapest Award, the University Senate accepted the proposal unanimously. I would like to quote Sir George Rada, our 2011 Semmelweis Budapest Award recipient. "Science has always been about the human endeavors and efforts which aimed at understanding the world around us, to solve the most important and fundamental problems, to discover new paths based on newly acquired knowledge. Serious science has never been a pastime. Let us simply think of Galilei, who struggled against prejudices and customs in order to promote new ideas which were based on the development of technology. That is not pastime. Science is still the same today. We are looking for new planets and stars to understand the genesis of the universe. We are working on new vaccines to eradicate one of the deadliest illnesses of Africa and other developing countries, malaria. Every one of these goals justifies the existence of science, and they provide scientists with a driving force. New, never-before-seen discoveries, observations and detections. Well, this is what makes science so interesting." These were the words of Sir George Rada. And now let me say a few words in the framework of a laudation about our today's awardee, Professor Maini. Before giving the floor to Professor Maini, it is very important to mention a couple of important things from his life and scientific activities. Professor Maini can be regarded as the father of the biological therapy, since he was the first to apply antibodies in human therapy. His outstanding research career has made a major contribution to improving the quality of life for people living with rheumatoid arthritis. Sir Maini was one half of a scientific partnership that developed the anti-TNF tumor necrosis factor biological therapy to combat inflammation and destruction of tissues in this debilitating disease. Their fundamental immunological research leading to breakthrough in treatment of rheumatoid arthritis and other related diseases was rewarded by the Royal Swedish Academy of Sciences with the Crawford Prize in 2000. As Sir Ravinder commented its significance, the discovery that inhibiting just one molecule could make such a huge difference to the many sufferers of this terrible disease was a truly remarkable find. It is extremely pleasing to find that our research has benefited so many and has been recognized through this award. For their discovery, Sir Maini, jointly with Professor Mark Feldman, also was honored by the prestigious Albert Lasker Award for Clinical Medical Research in 2003. The same year, Professor Maini was knighted for his work by Her Majesty Queen Elizabeth II in New Year's Honours List. Ravinder Maini was born in Ludhiana in the Punjab region of India in 1937, but has lived most of his life in the UK. He did his bachelor's degree at Sydney Sussex College in Cambridge and studied medicine at Cambridge University and Guy's Hospital, London. He received gold medal in clinical medicine, first prize in surgery and first prize in cardiology, all in 1962. He became a fellow of the Royal College of Physicians, London, in 1977. In his career, Sir Maini combined practice as a consultant in rheumatology and general medicine with laboratory-based immunological research. Dr. Maini had been associated with the Kennedy Institute of Rheumatology since 1979. He was head of the Division of Clinical Immunology from 1979 to 1989, then its scientific director from 1990 to 2002, lately head of Kennedy Institute of Rheumatology Division, Faculty of Medicine at Imperial College, London. In the 1980s, Dr. Maini and his colleague, Dr. Mark Feldman, identified TNF-alpha as a key cytokine in the process of rheumatoid arthritis. Together, they began to investigate the underlying biology of RA, an autoimmune disease. They found that the affected tissues harbored raised levels of an immune messenger molecule, the cytokine TNF-alpha. Normally protective, TNF-alpha was shown to be the major culprit of inflammation and tissue damage. Together, they proved that treatment with an antibody to TNF-alpha was remarkably effective at blocking the disease process and combating symptoms. Their first clinical trial was performed in 1992 at Charing Cross Hospital and revealed rapid and dramatic improvement of rheumatoid disease activity with the anti-TNF therapy. This paved the way for a series of larger European and US trials proving the effectiveness of TNF blockade and leading to the development of 3 anti-TNF drugs. The research now is an example of how innovative contributions from researchers who have combined basic research and clinical application have rapidly transferred findings from basic molecular research to new effective treatment, in this case of rheumatoid arthritis. They started from a clinical problem with the wish to find better treatment to a frequent and devastating disease. They searched the suitable experimental model where the basic critical observation was made. Then they pursued this observation in animal experiments, and eventually they completed the cycle by initiating and organizing the clinical trials. For me, this is the example how medical research should ideally proceed and proves the necessity of cooperation between experimental and clinical investigators. With systematic work for approximately 15 years, they succeeded to introduce a revolutionary therapy that changed the life of millions of people, the ultimate goal of medical research. Sir Maini has published over 480 papers and is co-editor-in-chief of the journal Arthritis Research and Therapy, and is a current member of the editorial board of Current Opinion in Rheumatology. His research in mechanisms of autoimmunity and immunotherapy of rheumatic diseases has been recognized by the award of honorary doctorates by the universities of Glasgow and Paris, and the Crawford Prize by the Royal Swedish Academy of Sciences, the Canadian Garner International Prize, and the Lasker Prize for Clinical Research. Sir Maini has served on numerous international scientific committees and is currently a member of the advisory board for the Center for Molecular Medicine, Karolinska Hospital, Stockholm, and the International Advisory Board of the Japan Rheumatology Foundation. Among others, Sir Maini is Fellow of the Royal Society, Fellow of the Academy of Medical Sciences, and Foreign Associate of the US Academy of Sciences. The scientific achievements of Sir Maini show to all of us how an outstanding principal investigator can move the world forward. It is of utmost pleasure to present the university's highest prize to him. And now I would like to ask Professor Maini to give his presentation entitled Development of Monoclonal Anti-TNF Therapy in the Search of a Cure. Professor Maini, please.
Dear Rector, Professor Seeley, dear colleagues, ladies and gentlemen. It is a real privilege to be standing here in front of you all. My affection for Hungarian science and the people that have been my friends or worked with me has no real measure. It's a real association of intellectual and emotional feelings for this country and its people. So I'm very happy to be so honored. Thank you. Now it is difficult in a short time to summarize the work that started in 1985 and came to fruition sometime in this century. What I will try and do is to pick out bits of the key steps in the development of this story and try and explain to you how we took risks and what the risks were, and how we overcame a lot of skepticism about what we were trying to do on the part of industry and on the part of our colleagues in science. So it was a difficult journey, and you never know how this journey will end till the journey is complete. And when in fact the journey was completed, both my colleague Mark Feldman and I were totally surprised that it took the direction that it did. And of greatest happiness to us is that maybe hundreds of thousands of patients have benefited from our discovery. That to us is the most significant achievement. So to the patients that took part in our research and to the clinical team that helped us to get the information we needed for our scientific work, I want to thank them. And they are usually not thanked, but without them we could not have done anything that we managed to do. So I just want to remind some of my friends that of course the rheumatologists here have been known to me for some years. In fact, I think since the 1980s. And here is the evidence, and I think the person who signed these certificates are in the audience, and they will remember that my association with the rheumatologists in Hungary actually dates back to many, many years. And some of them have worked in my laboratory and in the clinic, and it's been always a pleasure to have these people with us. Now, for those of you that do not come across rheumatoid arthritis, allow me to give you a very brief description of this disease. So, rheumatoid arthritis is characterized by inflammation and structural damage. So inflammation is mediated by immune cells, and if you look at the pathology of this inflammation, you find all the key players in immune inflammation represented in this world of this environment. Interestingly, it is a semi-autonomous system. So it is functioning semi-automatically and undertaking cell cooperation and releasing all the mediators of inflammation and tissue damage that is responsible for the unfolding scenario that we see over many years. Now, whilst inflammation is technically reversible, joint damage, which is mediated by osteoclasts and fibroblasts-like cells that invade cartilage and bone, much like cancer tissue, is irreversible. So that's a very important concept in understanding the natural history of rheumatoid arthritis. If you treat inflammation alone, but do not treat structural damage, the patient is temporarily feeling better, but in the long term, the disability follows an exponential curve. And that is how it was in the 1980s when Professor Feldman and I got together to undertake our studies. Now, rheumatoid arthritis is a common disease. It affects females more than males. And the important thing about it, when we started investigating new therapies, was that 50% of patients suffering from this disease were severely disabled by 10 years of the onset of disease. They were unable to work. If they were women, they were unable to do housework. So the social impact was enormous, and the social cost was enormous. And the problem was that the drugs we had were good for treating inflammation, but they were no good at halting structural damage. And as you will learn, anti-TNF was one of the first drugs which was able to demonstrate marked arrest of structural damage, even in patients in whom inflammation is not completely suppressed, demonstrating that these two processes are coordinated but independent. Now, what is not on this slide is that rheumatoid arthritis is a systemic disease. It can, of course, affect many parts of the body. And we don't have time to discuss that, but suffice it to know that patients with rheumatoid arthritis don't die from the arthritis. They die prematurely from vascular disease, coronary heart disease or strokes, or from cancer. And the cancer is at that of the lymph nodes, lymphomas. That is the aspect of the systemic nature of this disease, which is not often well appreciated. We don't have time to discuss that aspect of it today, and I'll confine my comments to the joint. So, the story starts in 1985, when Feldman and I, having previously worked with ill-characterized supernatant activities from cultured lymphocytes, became interested in what subsequently became known as cytokines. Now, cytokines were rather mysterious because they were biochemically not defined until the revolution which occurred in the 1980s, namely the development of the ability to clone DNA and to sequence proteins. Both of them had a huge impact on the discovery of new molecules and of new therapeutic principles like monoclonal antibodies. And it was that advance, that technical advance, that allowed accumulating knowledge to be applied. And that is a general principle, that technology often leads breakthroughs in science. Okay. Now, rheumatoid arthritis turned out to be a very interesting model for studying autoimmunity because tissue was readily available. In those days, rheumatoid arthritis patients were subjected to many surgical operations, so you could have kilograms of tissue, or you could biopsy tissue from using a telescope or needles. So it was accessible for study. Now, many studies are confined to blood, and it's insufficient because the site of disease is where you want to be studying. So we were lucky to be able to obtain access to such tissue. Now, the technical revolution that I described is highlighted here by the discovery of cytokines in 1980 through to 1984. Now, the reason that Feldman and I thought that cytokines would be important in rheumatoid arthritis was twofold. Firstly, gamma interferon was discovered to be a regulator of HLA antigens. And HLA antigens had been discovered to be essential in antigen presentation to T cells. And the evidence that had gathered at that point pointed to the likelihood that rheumatoid arthritis was a T cell-driven disease. So it seemed to us that cytokines might be implicated in this important autoimmune step, antigen recognition. The second reason was that interleukin-1 had been cloned, and work in many laboratories in the US and in the UK suggested that interleukin-1 might be a very important mediator of inflammation. So with that background, we began to study the spectrum of cytokines that were expressed in rheumatoid arthritis. So we were very fortunate in being able to access either cDNA probes or monoclonal antibodies, mainly from industry. And this technical revolution was occurring in places like Genentech and Immunex, not in university departments. That's an interesting fact. Anyway, they were very happy to give us these probes. So when we probed tissues from rheumatoid arthritis, we found that with any probe we used, we could demonstrate the presence of that cytokine. Now that's a very confusing picture, because cytokines are not only mediators of inflammation and immunity, but they have overlapping properties. That is what is called redundancy. There was a huge redundancy in the action of many of these cytokines that we were able to discover, telling us that these would be lousy as therapeutic targets. Because if you blocked one, something else would be able to do the same thing. Many other things would, in fact, many other factors would do the same thing. So we almost gave up on this project because we thought, this looks like a dead end, until one of the postdocs in our laboratory did an experiment which we had thought would be worth doing, which was to try and neutralize in an in vitro system of cells from rheumatoid joints all the neutralizing cytokine agents that we had. And we happened to have a very good neutralizing agent for TNF, interleukin-1, and GM-CSF. And to cut a long story short, what happened was that when you added anti-TNF to this culture system, the production of all cytokines that could be observed in this system over a week was abolished, telling us that there was in fact some hierarchy in the system. It was not a chaotic system, it was a hierarchical system. Okay, I will now show you some of the key data, and I won't spend time on this. First of all, here is the expression of TNF. You see it in the lining layer, mainly expressed by macrophages. And it is also expressed at the cartilage junction. Now there are two TNF receptors. Unlike TNF, which is localized to monocytes mainly, the receptor is expressed on every cell. So basically when TNF is produced in this joint, any adjacent cell that is in the vicinity of this produced molecule will have some effect on it. Hence it has very widespread effects. This is the experiment in which TNF reneutralization inhibited production of interleukin-1. Now, having done these two experiments, we felt we had to now do a physiological experiment, and that required an animal model. And it so happens that there is a very good model for rheumatoid arthritis called the collagen type 2 immunized mouse arthritis model. Now this mouse has a HLA molecule which is very similar to human beings, and collagen is presented as an autoimmune antigen, and this animal gets autoimmune arthritis. Now we were very lucky to be able to access a monoclonal anti-TNF antibody for mice, and when you gave these mice anti-TNF antibody, you could see suppression of inflammation. That is in here, dose response. Very strikingly, we observed protection of the joint, and if you look here, you will see the anti-TNF treated joints were very significantly normal looking compared to the controlled experiment. There's the normal joint. So this gave rise to this hypothesis that TNF neutralization suppressed the cytokine network. And we started to look for any company that would allow us to do the experiment in man. Okay, that was not as easy as you may think. Now, anti-TNF antibodies had been developed to treat sepsis. There was a lot of interest in the drug industry when work from 2 or 3 different laboratories demonstrated that this dreadful complication called septicemic shock that kills patients with septicemia can be treated by anti-TNF antibodies. And many companies in Europe and USA put a lot of money in trying to develop this treatment. It failed. That was a very timely failure for us, because one particular company that we knew well, because the head of that company had worked in London as a student, he knew our work, and he agreed, because there were shelves of unused anti-TNF antibodies that could no longer be used for sepsis trials. He said, okay guys, I'll give you enough for 10 patients. You go and do your experiment and tell me what you find. That is how we got anti-TNF antibodies. And this was in fact an antibody that had been developed at New York University by a man called Jan Wilczek. And Jan Wilczek developed this to treat sepsis. And the company with whom he cooperated had scientists that were able to chimerize it. Now this is important. The point is that up to then, monoclonal antibodies had only been from mice. And mouse proteins are immunogenic. So if you give a mouse protein to a human being, very quickly you build up antibodies to reject it, and the antibody is rejected. Which is why nobody thought that monoclonal antibodies could ever be used to treat a chronic disease. So when we were given this chimerized antibody, the company that developed this chimerization were able to join human immunoglobulin to 1/3 mouse immunoglobulin that recognized TNF. So it was less immunogenic, but still it was immunogenic. So the general feeling was this would be proof of principle, but no more than that. We were happy with that idea. And I want to show you the dramatic result we obtained in some of the patients. Now here's a girl with rheumatoid arthritis. All her joints are inflamed. No treatment is working. And she receives 1 shot of anti-TNF antibody. And I want you to see what happened to her. Okay, this is how she was before treatment with anti-TNF. 4 weeks after 20 milligrams of infliximab, CA2, the molecule that we were given, here she is. You know, scientists still believe what you see with your eyes. Okay, and we were seeing remarkable results when we were giving this antibody to patients with whom no other drug was working. So we were happy, but very quickly we realized that actually the benefit only lasts the duration that the antibody is present in the blood. The moment the antibody is used up, and it takes, depending on the dose, somewhere between 8 to 12 weeks, the disease comes back. So we knew this was not going to be a cure, and that for it to work would need repeated therapy. Well, so here's some data from the early work. Basically, we were able to show clinical efficacy and safety, and in a multi-center trial, we were able to show that a single dose of anti-TNF at the end of 4 weeks had a dose-response reduction in disease activity. with a p-value of less than 0.0001. There was no doubt that 80% of patients that received this antibody had a very good response. 20% had no response. That's important. No response. And we scratched our head. Maybe we didn't give up enough. We tried to give more. No response. Genuinely non-responsive. And we could, from this study, establish that you needed a serum concentration of 0.3 to 1 microgram for benefit, and that the best response required more than 10 micrograms per mil. Now, there is no way that you can estimate the amount of TNF that is produced in a patient. There is no way. Because it depends on how many joints are involved, how active the inflammation is. Basically, what you're trying to do is to give antibody in excess. So that can only be discovered by trial and error, by a dose-response experiment. And at this point, the company that we were working with said, very interesting, guys, we don't have any more money, so goodbye. So we said, well, hold on, because we have been back in the lab, and in this model of rheumatoid arthritis, we can show that co-therapy of anti-TNF and an anti-CD4 depleting antibody has a remarkable benefit and reduces the immunogenicity of the guinea pig monoclonal antibody that's given to mice. So maybe if you gave an immunosuppressive agent at the same time as giving the anti-TNF antibody, patients would tolerate it. So for 2 years, this company said, we don't have the money, but when we have some money, maybe you can help us to raise this money. So we went around, talked to other companies, big companies, and it was difficult, but eventually other companies became interested. And the experiment was done, whereby it turned out that the drug methotrexate, which was used extensively by rheumatologists, especially in the US, but to a less extent in Europe, was immunosuppressive in suppressing the immunity to this antibody called infliximab. So co-therapy with methotrexate allowed long-term treatment by suppressing immunogenicity and maintaining the blood value of this antibody in the serum. And the company was able to establish a dose that was economically practical, 3 milligrams per kilogram. Okay. Well, at that point we still thought this was interesting, but maybe it would be reserved for some very sick patients, would have a very limited use in the market. Now, unknown to us, many other companies were listening to this dialogue, and they also became very interested in this story. And one other company in particular became very interested and accelerated development with not an antibody, but a fusion protein, Tnf receptor IgG fusion, which is like an antibody, but is different. It has a lower affinity for TNF. Anyway, to cut another long story short, basically we were able to show that this drug resistance could be overcome with co-therapy with methotrexate, which turned out to be the case with all other anti-TNF monoclonal antibodies, because it maintains the serum level. And it's partly due to suppression of the antibody response to the drug, so-called anti-drug antibody. But there is something else happening with this co-therapy which we do not understand. Sorry. Have I lost? No. Can you hear me all right? Fine. Now it turns out that methotrexate accumulates in the cell, every cell, as a molecule called a polyglutamate. And polyglutamates exert multiple actions on various metabolic pathways. To this day, we do not know which cell is the most important cell that allows the pharmacokinetic of the antibody to be altered. But somehow, methotrexate delays the clearance of the antibody by the liver. So maybe it's acting on the liver cell or on some other cell that we do not understand. Okay, so that was the story up to that point. So what about these 20% that never respond? What's the reason for that? Here again is a riddle. A riddle means a question which we cannot answer. We can speculate as to why this may be the reason. It may be that the main pathway that is used for these 20% is not TNF dependent, but is dependent on some other molecule. And there is some evidence to support that. It could be lymphotoxin, it could be interleukin 6, interleukin 1, IL-17, or some other T-cell mediated interaction. Or it may be that non-immune pathways are involved. And recently people have become very interested in the role of the fibroblast in rheumatoid arthritis, previously thought to be an uninteresting cell. Now there is some reason to think that maybe these people are more dependent on the fibroblast than on the immune cell. Anyway, that is capable of investigation, and I'm sure we will get the answer in the near future. On the left are the key points. It works rapidly, with marked improvement in symptom signs and biomarkers. 70 to 80% of patients respond in the short term, but by 5 years or 10 years treatment, and you need ongoing treatment, only 40% of the patients that you started with are still responding, the others stop responding. So that's important to understand. It works, but for a proportion of patients it doesn't work. So it is not the most important drug for all rheumatoid arthritis patients. It is a very good drug. For 40% of patients that require it because they don't work with the other drugs that are cheaper, drugs like methotrexate. It is not universally indicated because it's very expensive. The annual cost of this drug is of the order of $12,000 to $15,000. So it is a heavy burden on any social system or person that has to pay for it. And we need to appreciate that these biological drugs are truly expensive. Now, it protects joints, and that's a very important point, because I told you that if you can protect a joint, the patients will go on functioning. And that is what happens. There have now been many studies demonstrating that patients who go on anti-TNF treatment before they become disabled are able to keep at work. And therefore, economically, they contribute more to the economy than before, which is the justification for what we call the cost benefit of this drug. But it does have some serious problems. It can cause serious infections. It can cause serious infections, especially tuberculosis and other intracellular infections. It does increase non-melanoma skin cancer, and sometimes it causes autoimmune diseases like multiple sclerosis. But fortunately, that is very rare. Now, initially there was a concern that it might increase the incidence of lymphoma. But we now know from registries that have been following hundreds of thousands of patients in Europe, US, and elsewhere, that that is not the case. And the reason that there was this signal was to do with the fact that rheumatoid arthritis by itself increases the liability to lymphoma. And of course, the patients we were treating in all the early trials had the most severe disease, and for the longest time, just the kind of patient who developed a lymphoma. So since then, Earlier in the onset of disease, patients are treated and that signal has disappeared. But there is still some discomfort on the part of some people that we are not 100% sure that it is completely safe from the point of view of lymphomas. So that's the reality. Now this is a timeline. I don't want to spend any time on it, but it just shows you how long it takes. We started in 1985 with the preclinical experiments. 1992 is the first patient treated in the clinic. Well, you saw one of the first patients coming down the stairs. And it's not till 1998 that that drug is licensed for treatment, and not until 2002 that this organization called NICE in England, which evaluates the cost effectiveness of drugs, allows it to be prescribed on the National Health Service. Okay? So it takes a long time for this drug to make its way to the clinic. But it becomes very successful. So successful that lookalike drugs develop. So by 2014, there are 5 anti-TNF drugs. Today, there are 9 anti-TNF drugs. And why do you think that is? It is because it works not only for rheumatoid arthritis, but for many other conditions which are on this list. So the one drug size fits all is the reason for its success. Okay, that's nice. There are not many drugs that you can prescribe for many different diseases. This one is such a drug. And here's an important other reason. This is a chart of the blockbuster drugs in 2015. And there are 3 anti-TNF drugs that are in the top selling drugs in the world. In the top 7. Okay? Here's one, here's a second, here's a third. 1 to 7 out of 200 drugs. Annual turnover of $30 billion. So, of course, people would be delighted to be making a drug that makes so much money. So that is the other reason that biologicals became so successful. Now, what lessons did we learn from this work? Now, here are some. When Feldman and I started the work, you could talk to the biotechnology industry and say, hey, you pick up a phone, I hear you've got a TNF cDNA. Can we use it? Can you give us some? Sure, you can have it. It arrives in the mail. You can do the experiment, you thank them for the reagent. Fantastic. It's no longer the case. You want something from anybody now? You have to undergo a long procedure of signing documents that if anything is discovered, the intellectual property does not belong to you, it belongs to the company that gives you that reagent. Yeah? So, the innocent scientific age that we enjoyed has ended. And that's sad. What has happened instead is that researchers now have to learn to be business people. And I mean this. I think if you are a young researcher that is in discovery, you really need to understand how patents are made, how ideas can be commercialized, so that you and the university retain some of the rights. And that is a difficult lesson, because it also needs money and expertise. It needs legal expertise, it needs business expertise. Now, most universities in the US woke up to this 20 years ago. In the UK, they've woken up to it in the last 5 years or 10 years. But only a few of them have woken up to realize that the expertise is a very significant expertise, and the money is serious. No drug that is a therapeutic can make money until you show, at least in a phase 1 trial, that it is safe. Ideally, you want to take it up to phase 2 to show that there is some signal that it might work in the disease for which you want that drug. At that point, you have valuable asset. And researchers need to understand, and universities need to embrace the vehicles that allow commercialization. Oxford now has a very well-oiled machine, and there are lots of funds that have been set up with companies, big and small, intermediate companies that will take things up to a certain level, because big companies don't have time for this, right? So the risk has to be taken by someone else. And usually that risk is taken by investors. And so nowadays the big companies will put some money into it with a licensing agreement. But please understand how this works. So for the young people that are in this audience, that are doing research that might lead to a new discovery, this is important to understand. Now, how does it work? And I want to briefly tell you that this was a uniquely interesting experiment because you have a highly targeted drug. It blocks TNF and nothing else. So you can study how it works. And there are two things we discovered very early on. Firstly, that it blocks the production of interleukin-6, which is a very important mediator of inflammation. It works immediately, within hours of giving anti-TNF antibody, interleukin-6 production by the liver cells shuts down. Oh, and I've broken this thing. Sorry. Okay. And what this means is that you have actually demonstrated in vivo that there is a network connection. We thought from preclinical experiments interleukin-1 was important, but in real life it turns out that interleukin-6 is more important than interleukin-1. Interleukin-1 is modulated, but not to a great extent. Okay. So the next slide shows you that the other important effect is on the trafficking of cells into the joint. And this has been shown by two kinds of experiment. In one, on the left, we have done biopsies of joints before and after giving anti-TNF antibody and looked at markers. And the markers showed that interleukin-8 and MCP1 is the monocyte factor, is depressed. These E-selectin and VCAM, which are adhesion molecules, are reduced. And the angiogenic factor of VEGF is reduced. And here's the direct evidence that it does something to trafficking. So in this experiment, we have labeled white cells with indium 131, which is the gamma emitter, and you inject the cells back into the patient. Before anti-TNF treatment, the cells are retained in the knees, wrists, and finger joints. This is a readout of the radiation. 2 weeks after an anti-TNF injection, you repeat the experiment, and you see there's no retention, or very little retention. And this is telling you that the cells are no longer stopping in the joints. Okay, so that's the other major effect of this therapy. Now there are many other. In Crohn's disease, inflammatory bowel disease, this antibody apoptoses some of the mononuclear cells in the gut, but not in rheumatoid arthritis to any significant extent. It inhibits angiogenesis, inhibits cartilage and bone destruction. It partially restores homeostasis. And in this very interesting experiment done in Germany, using fMRI on the brain, one injection of infliximab is followed by reduction in activity in the nociceptive response in the brain, the part of the brain that feels pain, almost instantly, within hours of the anti-TNF. There is a central nervous system effect. So it is not surprising that these patients were telling us that they're feeling good, because their brain is telling them that you're feeling good. Okay, we always suspected there was a central nervous system effect. Now you can demonstrate it. Okay. Well, this discovery has had a miraculous effect on the production of biological agents. They have multiplied. Okay? Today, biological drugs are competing with chemical drugs, one for one. For every one new drug that is going on the market, which is a chemical, there is one new biological that is going on the market. So it has completely revolutionized the treatment of cancer, inflammation, and other diseases. So we are now in a new era. And there can be no doubt that anti-TNF was the proof of principle that convinced the drug industry that this was where you should put money. Okay? Great. I'm not sure whether it will last, because in the end, receiving something by injection every 2 weeks or every 4 weeks, or going to a clinic for an intravenous infusion, is that as good as taking a pill? Not. Probably it's easier to take a pill. So if pills are found, and now there are some pills, like JAK inhibitors, tyrosine kinase inhibitors, that are effective in rheumatoid arthritis, but probably their safety is not fully understood, because hundreds of thousands of patients haven't yet been treated for 15 years with JAK inhibitors, which is the case for anti-TNF. So we have a public record of safety which is unequaled for any other drug, because people became very interested in safety of medicines, where the safety signal requires not 200 patients to be treated, but 20,000 patients to be treated before you could be sure how safe it is. So one day we will discover whether these tyrosine kinase inhibitors truly are as safe as these biologicals, in which case they will take off. But we don't yet know that. Okay. So we obviously have not cured rheumatoid arthritis. So how will we cure it? Remember I said at the beginning of my lecture that technology is the key step that leads to new innovation. So technology is happening on a grand scale at the moment. I think all the colleagues here who are still working at the bench know exactly what I'm talking about. There is technology today like sequencing the whole human genome that is available for less than $1,000. So you can look at the whole genome, which you couldn't do before, in less than maybe 6 months, costing a lot of money. So suddenly you can look at the human genome of individual patients. You can look at 40 markers on a single cell. Okay? 40 ligands on a single cell. On one drop of blood, you can look at 2,000 analytes, most of them with unknown function. And you can imagine doing longitudinal studies with these biomarkers, creating terabyte of information on 10 or 15 patients. How are you going to analyze it? Well, you will need big data analysis, you will need artificial intelligence. And take my word for it, they are both developing in a very big way in biology. So last night I had the privilege of being entertained by a young researcher, Thomas. Where is he? Thomas is here. There he is. And I told Thomas, if you go abroad, make sure that the place you go to understands how to handle big data, because that is essential for the next phase of innovation and discovery. So if you go somewhere where big data analysis is not part of what is available, forget it. Don't go there. You're wasting your time. Okay? So biomarkers are now needed in order that you stratify patients. Because it turns out that 20-30% of patients don't respond to anti-TNF. You want to know that before you start anti-TNF therapy. There are patients that get bad responses to drugs. You want to know that before you start. All that will be possible by the use of biomarkers. Initially, it will be in groups of patients, stratification, and that's already happening in cancer and in rheumatology. But in 10 years' time or 5 years' time, it will be personalized. Every individual patient will carry a chip. So under the skin, you will have a chip. And the chip will have your whole genome on it. It will have information about all the important biological data that you have developed since childbirth, maybe in utero as well. Because we know even in utero imprint leaves a legacy. With that information, you should be able to individualize treatment. Is that a hopeless dream? I don't think so. I think it will be feasible, provided there is a political will and cooperation between scientists, clinicians, and enlightened political governments. I have to say, I have some doubts about the politics, seeing what is happening in the world. So, will this happen? I don't know. I hope it will. And it is with that spirit that I say to all of you, thank you for listening. It's been wonderful being here. I think the future is bright, and thank you for honoring me.
Professor Maini, these moments here, this half an hour or so, was really a wonderful time for us. I think that we have learned a lot. I liked it very much how you have moved from the bench to the bed, from the bed to the business, and then back to the bench, and then to the big data. Many four or five words starting with the T. I think that these are key words. And it also reflects the complexity of science. You have to be a businessman, you have to be probably a lawyer as far as the patents are concerned, you have to be a medical doctor, you have to be an extremely good laboratory. So it is a fantastic line of science which we try to follow if possible, and I think that if for nothing else then just for such experiments, experiences like this one here now that we have learned from you, it was worthwhile introducing this Semmelweis Budapest Award. And after really appreciating your efforts, not only in your science but also in the way how you have taught us about these things, let me give you this honor, and let me feel that probably it is not only you who is honored, we are honored that you have accepted this thing. Let me give it to you, and congratulations for this wonderful work.
Thank you.
Thank you very much. Once more.